Hello, everyone. My name is Hércules de Melo Barcelos, and I am a researcher for National Institute of Metrology, Quality, and Technology in Metro. Well, today I'm going to talk about the recalculation of internal directional derivatives use the integral equation of the boundary element method in Poisson problems previously solved by the finite element method. The co-authors of these works are researchers Carlos Frederic Loffe and Luciano de Oliveira Castro Lara, both professors at the Federal University of Espírito Santo. Well, the presentation is divided into 5 main sections. These are recursive boundary element process, RBEM, are being applied to Poisson problems, complete procedure FEM RBEM, numerical simulations, conclusions, and reference. I will start some general information on RBEM. RBEM is the recursive scheme was already present at CILAMCE last year. However, it's important to review it. The RBEM is a process that uses the integral boundary equations, no calculation the values of potential and normal derivatives for a certain domain. Using for this the nodal boundary values previously obtained through the linear system generates with the application of the BEM. Good results were obtained in scalar on elastic problems, having examples the solutions found for modules governed by the equations Laplace, Poisson, and Navier equations. The idea behind the process is associated with a new minimization of errors with the reuse of the integral sense of BEM, since it is associated with a synthesis of weighting residuals, where the minimizations of errors is done. There rules when observing at the values calculate internally had higher precisions when compared to the values obtained in the boundary. I would like to show you this. Once now the classic integral synthesis of the BEM for Laplace problems, it is possible to construct the matrix system HU equals GQ, and from it calculate the values of UX and QX previously known in the boundary. The values of the internal potential can be calculated by reusing the integral synthesis with all known values of UX and QX at the boundary. Internal derivatives can be obtained by deriving the integral synthesis for the potential with respect to the source point C. The new terms obtained are present on this slide. In the second section, if you look up at the screen, we added the term Px corresponding to the source term for the Poisson equation. The equation for calculating the internal potential presents a term that must be transformed into a line integral. It was present in the submet article to choice of a primitive function for the fundamental solution, and that by simplifying the model, considering null the term null, the Laplacian of Px. And thus, the internal potential is found and the new terms are present below. As done in Laplace problems, the directional derivative is obtained by deriving the expression for the calculation of internal potential, give rise two new terms related to the galactic tensor. In this third section, I used to show you this. The coupling procedure FEM-RB. Based on previous experience, it was found that use of RB is effective for the calculation of internal values, whether potential or derived from the potential. With this, the application of RB for the calculation of internal derivatives in problems solved by the finite element method was motivated. The motivation is based on the following information. We know that the classical formulation FEM uses shape functions to make the distribution of potentials. We also know that these functions are derivable, which brings a clear loss of precision in the calculation of derivatives. Thus, the FEM boundary values were obtained using meshes with low refinement. These values were used during the reuse of the RB integral equation, and with this, the internal derivatives at source points with arbitrary position were calculated. In this fourth section, I want to show you this. Numerical tests were performed using structural meshes, and the error measuring tools was the mean relative errors. The RB is advantageous for meshes with low refinement. However, meshes with higher refinement were used precisely to measure the convergence of the recursive procedure. This first test was added precisely to show the convergence of the method for Poisson problems with constant load. You can see the analytical solution and the error curves for calculating the internal derivatives. Observe the error curves generated for FEM, BEM, FEM, BEM in the graph. In this verified that for mesh 1, that the FEM-RB coupling improves the results when compared with the results obtained by the FEM. The second test was present in article and represents the Poisson problems with variable load. This is example, we have the analytical solutions and the error curves for calculating the internal derivatives. Note that performance of the FEM-RB for meshes with low refinement is still superior to traditional FEM. For both problems, it is possible to observe the convergence of methods. Finally, at 5 section conclusions. Basically, that's what we wanted to present. Good results were found for the position problems, and the association for FEM-RB was advantageous. It is important to comment on two important factors in using FEM-RB. The first is association with a low computational cost. Since to calculate each internal point, only the RB equation is used. The second point is associated with the freedom to choose the position and the number of internal points that only wishes to obtain an answer. Well, these are the references for this work. So, thank you all for the attention.